By age 13, Demis Hassabis was the second highest-rated chess player in the world for his age bracket. But as he looked around at international tournaments, he had a realization. Hundreds of brilliant human brains were dedicating their entire lives to mastering a single, isolated board game. It seemed like a massive waste of cognitive potential. When he arrived at Cambridge University, his obsession shifted from playing games to understanding the player. He wanted to know how the human brain actually computes information and how it seamlessly learns across entirely different subjects, from mathematics to art to biology. At the time, the leading artificial intelligence systems operated very differently. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov. It was a staggering technical achievement, but the system was incredibly narrow. Deep Blue could beat a grandmaster at chess, but it couldn't learn to play checkers or even tie a shoe. This diagram illustrates the concept that became DeepMind's central thesis. Instead of building narrow systems, they pursued artificial general intelligence, or AGI. The goal was to write a single algorithm that starts with exactly zero knowledge, yet possesses the capacity to learn and master any problem you hand it. To build this universal mind, scientists couldn't just release it into the real world. They needed a laboratory, a closed, highly controlled simulation where a fledgling AI could experiment, fail, and learn millions of times without causing actual physical damage. They found their perfect closed-loop environment in vintage video games. The training parameters were ruthlessly minimal. The system wasn't told the rules, what the controls did, or even what it was supposed to achieve. It was simply fed the raw pixels on the screen and given a single mathematical mandate: maximize the score. Within hours of chaotic trial and error, it taught itself to play with flawless, superhuman speed. What made this remarkable was the scalability. Without altering a single line of code, the exact same algorithm learned to conquer dozens of entirely different virtual environments. The system used a single digital brain to figure out everything from scratch. This was achieved through a process called reinforcement learning. Much like training an animal, the algorithm navigates its environment through a strict system of digital rewards and punishments. Every action that increases the score strengthens a neural pathway, while every mistake prunes it away. But deep down, the team didn't actually care about high scores on vintage consoles. These virtual worlds were merely an incubator. They were raising an intelligence, preparing it to eventually interact with physical reality. The final virtual hurdle was the ancient board game Go. For decades, computer scientists considered it uncomputable. There are more possible board configurations in Go than there are atoms in the observable universe, making brute force calculation useless. In 2016, DeepMind's AlphaGo system faced world champion Lee et al. During the match, the AI played Move 37, a strategy so alien that commentators assumed it was a glitch. The system calculated a 1 in 10,000 probability that a human would ever make that move. The AI had discovered a genuinely novel way to play a game studied for thousands of years. They pushed the concept further with the next iteration, AlphaZero. They removed the database of human games completely. Given nothing but the rules, the system learned strictly by playing against itself. Starting from random noise, it became its own teacher. For China, watching this system invent strategies in real time was a Sputnik moment. It triggered an immediate shift in national policy and billions in research funding, signaling that the technological lead in intelligence was no longer guaranteed to any single nation. DeepMind had successfully engineered a system that could generate novel, highly effective knowledge inside a simulation. It was finally time to point this engine at the real world. They targeted one of the most stubborn mysteries in biology, the protein folding problem. For half a century, scientists tried to predict how proteins form, a puzzle directly tied to discovering new drugs and understanding life itself. Proteins start as a 1D string of amino acids that must contort into a specific 3D puzzle piece to function. Mapping this in a lab takes years per protein. The math is staggering. Possible folding configurations exceed the atoms in the universe. DeepMind entered their system into a global protein folding competition, and initially, it failed. They quickly realized that physical reality is messy. You cannot solve biological mysteries with raw compute power and trial and error alone. The team adapted. They assembled a strike team to integrate the actual laws of physics and biological constraints directly into the neural network. They had to teach the algorithm how to bridge the gap between pure math and physical matter. The result was AlphaFold. In a matter of months, the revised system achieved what human researchers couldn't manage in 5 decades, proving that generalized AI principles can decode the complex physical laws of nature. DeepMind mapped 200 million protein structures, nearly every known sequence in existence, and made the database free for anyone to use. This provided the global scientific community with a tool that accelerated projects that had been stalled for decades. This transition from mastering board games to decoding biological systems marks a shift in what artificial systems can achieve. It demonstrates that the same logic used to play Atari can be transferred to solve the most complex physical challenges our species has ever encountered. But an algorithm that can understand biological folding can also be pointed toward harm. The potential for military abuse, hyperscale surveillance, and conflicts that escalate faster than human comprehension is a practical, near-term reality. The same logic used to predict a life-saving medicine can also be utilized to design a potent toxin or a novel biological agent. DeepMind's leadership has acknowledged this duality, suggesting we are handling a force that requires the same level of global coordination as the atomic age. The standard tech industry ethos of move fast and break things fails when applied to an intelligence that rivals our own. We cannot afford to deploy an irreversible technology and hope to patch the consequences after the fact. Humanity stands at a critical historical crossroads. It requires immense ethical stewardship to ensure that we remain the masters of this technology and that our most powerful tool does not become our final invention.